All right, so now we're going to sketch the algorithm for both Jacobi and Gauss-Seidel. And the reason why I'm going to discuss them together is because the code for it is essentially the same except for a slight tweak in one position. Okay. So the algorithm for Jacobi iteration for approximately solving ax is equal to b, okay, is as follows. It has the following input, okay. It has the A matrix, the right-hand side B, M is the size of the matrix M, XO is the initial iterate, there's a tolerance, and then N is the maximum number of iterations. And the output is X, which is my solution, and N is the number of iterations I took. Okay, so I first let N equals to 0, and I create a flag to determine when to stop, and I set that to 0 first. So while the number of iterates is less than equal to the maximum number of iterates big N, and I have not flagged to stop it, then I perform the iteration. Okay, so for I equals 1 to M, I do the following. So if you recall, it's like what you have to do is you have to compute this right-hand side, and then you have to divide it by the diagonal entry. Okay, so the first part has to do with computing that b minus the sum term. Okay, all right, so let's have a temp counter be 0, and then I go from j equals to 1 to I minus 1, right? Temp is equal to temp plus aij times xoj, and then the end. And then for j equals to I plus 1 to M, again, I add the entries from this product here, right? aij xoj, end, okay. And then now xi, which is the I component of the new value of x, is equal to bi minus this temp, and then the whole thing divided by the diagonal entry aii. Okay, all right, so that's the new solution. And then if I go over all I have the whole right hand side. So now I can check the condition. So if x minus xo is less than some tolerance, right, then I can stop. I mean, in principle, it's also possible to compute the residual error, right, which is a times x minus b, and look at the norm of that. But that's kind of an expensive thing to compute, so we're going to try to avoid doing that. Okay, all right, and then xo is equal to x, so sorry, x equals xo. Yeah, xo is equal to x. So when I cycle through it again, it's like the new value becomes the old value of the iteration. And then n equals to n plus 1, and then I end the loop. Sorry. All right, so that's basically the Jacobi iteration, okay? And it's really not that different from the Gauss-Seidel iteration, because if you recall, it's like with the Gauss-Seidel iteration, the main thing which happens is that when you do this product here, instead of using the old values, right, for for the things you've already computed before, you use the new value. Okay. So there's really not a whole lot of difference between the Jacobi and Gauss-Seidel iteration. So let me just have you look at this, and then I'm going to change basically just two parts of it. I'm going to change Jacobi to Gauss-Seidel, and I'm going to change this entry here. Okay. So the bottom line is that if you code up the Jacobi iteration and you want the Gauss-Seidel code, you only need to change this entry in your code. Okay, so I'm going to go ahead and do that now. So now this is for Gauss-Seidel. All right, and then this entry, instead of XO, becomes X, right? Because if you recall, XO is containing the nth iterate, and X is containing the nth plus first iterate. So for all these entries, which involve the x's, which are from 1 to I minus 1, which were the things you've already computed, I can actually use X instead, the nth plus first iterate instead of the nth iterate to compute the nth plus first iterate for the ith component. Okay, so that's literally the only difference in the code to go from Jacobi to Gauss-Seidel. Okay, so that's relatively straightforward. And if you recall, I sort of alluded to this idea that there's another variant of Gauss-Seidel. It's like where instead of looking at the lower triangular part, you can look at the upper triangular part of A, and then that involves something like back substitution. And so intuitively, it's like what would happen is that you would have, instead of I going from 1 to m, you go from I equals to m to down to 1. And then, as before, it's like you have these two, you have to break it out into to do these two parts. It's like, and you just have to make sure that you're using the updated value for the i's, the values of j, which are bigger than I now, right? So that's the main difference. Okay. So anyway, so hopefully it's like you get an idea of what the code is really doing. It's a relatively straightforward thing. And I should remark that many of these operations can be again vectorized, because of course this thing here, I mean this whole thing, if you will, is essentially computing the dot product of a component of the part of a segment of the matrix and this part of the vector as well. So you can rewrite these things. It's like by appropriately sort of extracting the relevant part of the A matrix and then doing some sort of dot product with a part of the vector as well. Okay, so yeah, so a lot of times for loops can be replaced with vectorized code. I mean, if anyone is interested, I'll be happy to talk to you more during office hours. But it's like this is sort of the the simplest way of implementing this, and it's agnostic to the type of programming language it's like you might want to implement this on. But if you happen to be implementing this on MATLAB, then it's like a lot of speed. It's like can be it can be substantial speed improvements. It's like by constructing a vectorized version of the code. So anyway, so let me just stop here for now.